So our next speaker, the final speaker of the morning session, is Luiza Tenorio from the University of Rio de Janeiro, and she'll be speaking on sheaves on rings and Czech cohomology.
Thank you, Richard, for having me and for organizing this event. So the title is Sheaves on Rings and Czech cohomology, but actually I'm going to talk about sheaves on quantales. So this is a part of my PhD thesis, which I recently concluded in the University of São Paulo, but now I'm at the University of Rio de Janeiro. And this is a joint work with Hugo Mariano and Peter Arndt. So let's talk about sheaves on topological space first, because I want to compare with those. So fix a topological space X and consider the set of open subsets of this topological space. And we can see this as a category using the inclusions as morphisms. And then a presheaf with values in set is just a functor from the opposite of this category to the category of sets. And the presheaf will be a sheaf if for each covering of any open of our topological space, you're going to have an equalizer diagram of this form. So what is important for us here is that we have this equalizer diagram, we have an intersection here, and we have this notion of a covering that is given by the unions of smaller opens. And so in case you never saw sheaf before, I think it's important to give an example. So I'm going to give you the most famous example, and a simple one is the sheaf of continuous functions. So we have two topological spaces, and we have the set that goes from x to I, y, and those functions are continuous. If you have an open subset U of our topological space X, we can have now a set that goes from U to Y, and again, our functions are continuous. But if you have two open subsets where U is included in V, we are able to define a map that takes this continuous function that is defined on V and just restricted it to U. And this is going to give us a presheaf. And this is a sheaf basically because if you have a covering of U given by these UIs, and we have continuous functions defined on the UIs, and I take Fi and Fj, when I restrict them, I will have that they coincide in the restriction for the intersection UI intersected with Uj. And then I will be able to obtain a unique continuous function F from the unions of UIs, so for our U here, such that the Fi's coincide with F restricted to each one of the UIs. So this is what gives us a sheaf. This is the translation basically of the definition using equalizer diagrams. And I want to mention that there is another example of a sheaf given by the structure sheaf that appears in algebraic geometry. But here we start with a ring, and this ring is commutative and has unity. And we consider the spectrum of it given by all the prime ideals of this ring. And this can be seen as a topological space under the Zariski topology. So here, if you take element F of a ring, we can consider a set of prime ideals that do not contain this element F. And this is going to form an open basis. So how to describe this sheaf? I'm not going to prove that this is a sheaf, but the idea is that we are going to take these open bases here, and then we can send this to the localization of the ring for this element. Since this is a sheaf, basically we have that this diagram is an equalizer. If we apply this definition of the sheaf, and using that we have this equality, this basically gives us that this diagram here also is an equalizer. So I just using here to obtain these isomorphisms here. Those here are isomorphic to this one, and this guy here is isomorphic to this one. That's why we have an equalizer diagram here. So hold this information for a moment. And now consider the set of principal ideals of a ring, commutative with ring always. we are going to define a sheaf, but not a sheaf of sets, but a sheaf of commutative rings. We have changed the category here. And what we're going to do is to now take the principal ideal and send it to its the localization of the ring. So we said that this diagram here is an equalizer, but it's also known that we have an equality like this. So what we have when we apply the definition of this functor is that we have an equalizer diagram of this form. So the idea is that we are trying to see this functor here as a kind of a sheaf, but instead of having intersections here, we have a multiplication, a product of the ideals. So, and also we are using that the set of principal ideals is some kind of base for the set of all ideals of our commutative ring. So if you want to define sheaves on a ring, maybe what we should do is to consider now the set of all ideals of a ring and see this as a category. And again, there are the relations that will be given by inclusion. Again, the presheaf will just be a functor like this. But now sheaf is a presheaf if for each covering, and now the covering is in the format of a sum of ideals. We are going to have an equalizer diagram of this form where we just replace the intersection with the product of ideals. So our question here is how to define sheaves on topological spaces and sheaves on commutative rings with unity using a same general framework. And to do this, we use quantales. So in case you don't know, a quantale is a completely lattice with a monoidal structure where the multiplication of this monoid distributes under the supremums of the lattice. And I notice here that when the multiplication is the infimum operation, then the quantale actually is something that we call a local. So some examples of quantales. We have the set of open subsets of our topological space, where the multiplication is given by intersection. I notice that intersections are an infimum operation. So actually, this quantale here is a local, and sheaves on locals are pretty well known, and they are already well studied. Another example of a quantale, but this one is not a local, is given by the ideals of the ring, and the multiplication is the product of ideals. And the last example here is given by the interval from 0 to infinity, but the order is the greater or equal, and actually the multiplication is just the sum. So a presheaf will be a sheaf when we have a covering, and a covering will be the supremum here. So just to be clear about this, in the case of topological spaces, the union is a supremum. In the case of rings, the sum is a supremum. And it will be a sheaf if we have an equalizer diagram of this form here. So when we have an infimum, this gives us exactly the definition of a sheaf on a local. So when you try to define things in this way, we just have to be sure that these parallel arrows here exist. And to guarantee this, we impose an extra condition in our quantales. This condition says that if we have the multiplication of two elements in the quantale, I want this to be less or equal to each one of the components. So if I have this less or equal, when I apply the contravariant functor, the presheaf, I will have arrows in this direction, and this will guarantee to us that those parallel arrows here exist, so our definition at least makes sense. So let me talk about some other properties about quantales. They can be commutative, and for our definition, we don't need to use that our quantales are commutative, but for the rest part of this presentation, I always assume that our quantales are also commutative. Then can be idempotent, but in general, in our case, we don't want this. And they can be semi-Cartesian. So the semi-Cartesian property is this one about the product being less or equal to each one of the components. And this is equivalent to saying that the unity of the monoid is equal to the top element of the quantale. And just one last example of quantales it is given by the closed right or left ideals of a C-star algebra, where the multiplication is the closure of the product of ideals. So this is basically the example that made the theory of quantales start with movie, but we don't use this one because this example is an idempotent one, but not semi-Cartesian. And a small remark here is that when a quantale is semi-Cartesian and idempotent at the same time, then the multiplication has to be the infinite. So the quantale necessarily is the local. So that's why, in general, since we're already assuming that our quantales are semi-Cartesian, we don't ask them to be idempotent. And for clarity, another name for semi-Cartesian in the literature is integral too. So they have those two names for basically the same thing. So some warnings here. We are constructing this theory of sheaves on quantales, where the morphisms are given by natural transformations. But in general, we are not going to have that this category is a topos. And why this happens? Basically, we have proved that the completed lattice of the subobjects of the terminal sheaf is quantalic isomorphic to the quantale itself. It is known that we have the subobjects of any object of a topos. This has a heightened algebra structure. So what is happening here is that if your quantale doesn't have this underlying heightened algebra structure, then we cannot have that the sheaf on this quantale will form a topos. Another theorem that we have here is that if we consider the inclusion from sheaves on quantales to the category of presheaves on the quantale, it will have a left adjoint functor, and we are going to call this left adjoint functor the sheafification. But what is important to have in mind here is that our sheafification does not preserve all finite limits, because if it preserves all finite limits, then we would obtain a growth-in-V topos, and all growth-in-V topos are topos. And we already know that in some cases, this category of sheaves on quantales is not a topos. But this sheafification does preserve the monoidal structure in the category of presheaves on the quantale, and given by the day convolution. And when I say this, I say actually that our category of sheaves on quantale is a monoidal closed category. So these are our warnings to have in mind here. Now I want to give us some technology to talk about what is going to happen in our Czech cohomology. And for this, I introduce this notion of a geometric morphism between quantales. It will be a map that preserves arbitrary subs and unity, and that also weakly preserves the multiplication. And by this, I mean that I have this inequality. And this geometric morphism will be strong when actually this is not an inequality, but is an equality. So we preserve the multiplication. Some examples of a strong geometric morphism is when we have the idempotence of the quantale and goes to a quantale just using inclusion. And also for every surjective homomorphism from between two commutative and unitary rings, this is also going to induce a strong geometric morphism. So why this is important, this kind of morphisms, is because if you have a geometric morphism and we have a sheaf in the contra-domain here, in the contra-domain quantale, we will be able to obtain a new sheaf, but now for this other quantale, the quantale in domain. How to prove this? We just have to take a cover in the domain quantale. Since our geometric morphism preserves supremo, this is going to give us a cover in the other quantale. And also why the inequality is important is because since F is a sheaf, we are going to have that this diagram here, in this way, is an equalizer diagram. And because of this inequality, we have that this triangle here commutes, and this will give us that this equalizer here is also equalizer diagram. So the precomposition forms a new sheaf. In particular, we are going to be interested in those in one specific kind of strong geometric morphism. So we're going to fix a topological space, and I want this to admit partition of units subordinate to a cover. This happens, for example, for any topological space that is paracompact. And I want to consider the ring of real-valued continuous functions on this topological space. And I'm going to define a functor that goes from the ideals of this ring to the open subsets of the topological space, and another one in the other way around. And what is important is that tau is going to be a left adjoint to the theta, also that tau is a strong geometric morphism, and theta is a geometric morphism. So what is happening here is that we have a sheaf here on the topological space. Tau is going to give us, by precomposition, another sheaf, but now for the quantale of the ideals of this ring. In particular, if we consider the constant sheaf defined for the topological space, this is going to induce a sheaf for the ring. It's not clear at the first sight, at least, if this induced sheaf is some kind of constant sheaf or not. But it will be, because those conditions here are so good that will give us that a diagram of these forms commutes up to natural isomorphisms. So if you are taking a constant functor for the ring, it should go in this way. But if you take a constant functor for the topological space, it goes this way. But then we can apply the precomposition by tau, and by that theorem, we have that this gives us a sheaf again. And by the commutative of this diagram, we're going to have that the induced sheaf actually is isomorphic to the constant sheaf in this category. And so now I can finally talk about Čech cohomology. And the idea is to be naive again. So basically, we are taking abelian sheaves, but now on the quantales instead of just topological spaces. We want to fix a cover. And now we're going to have a Čech chain complex for the cover and with coefficients in the sheaf, given by these products. So I just want to say that when you have this product here to be the intersection, so when you're dealing with the open subset of a topological space, this is precisely the Čech chain complex for topological spaces. And also the comboundary morphisms will be basically the same, given by the same kind of alternative sum. And then the Čech cohomology will be defined just by the quotients of the kernels and the imaging. Then we have a theorem. If you have a strong geometric morphism, we will be able to relate the Čech cohomology of one covering to the Čech cohomology for all the other covering induced by our geometric morphism. And the proof is not difficult actually. We just have to apply the definition, and we would obtain something of this form. Since you have a strong geometric morphism, this preserves the multiplication. So we have this line here, and then we just apply the definition again, and it appears the other Čech cohomology complex. This will give us a diagram that commutes of this form. And because this is commutative and we just have identities here, actually have that the Čech cohomology coincides. So, but the problem here is that usually we don't want to talk about Čech cohomology of a covering. We want to talk about Čech cohomology of the topological space. So the topological space is an element of the local or the quantale more generally. And to define then this Čech homology for the elements instead of taking the covering, what you have to do is to consider a certain co-limits of the previously Čech homology groups. And under these circumstances, we will also be able to relate the Čech homology groups between two different quantales, but we have to impose some other conditions. We need to have a strong geometric morphism, and since it preserves supremos, by the adjoint theorem, we know that we be able to obtain a right adjoint functor. And I want this right adjoint functor to preserve unity and arbitrary joints. And under this circumstance, I will be able to establish isomorphisms between the Czech homology groups for one quantale and the other quantale. And those ones here, just to remind you, they are just the top elements, unity elements of our quantales. So how to prove this? So I'll just sketch the proof here. Basically, we apply the definition again. We have these colimits. By the previous theorem, I am able to establish that this guy here is equal to this one. So we have those actually isomorphisms between those colimits. As we are able to prove that this composition here is going to give a refinement of the covariant U. And this will imply that we have that this covariant is contained in this other covariant. And then this is going to give us by some kind of cofinality argument that this colimit is actually isomorphic to this colimit here. And this one was exactly the one that appeared here. That's why we obtain isomorphisms between these cohomology groups and these Czech homology groups here. So we want to apply this theorem to have some kind of situation that is interesting. And the situation is for those functors tau, where we had that this was a strong geometry, and we had theta that was just a geometric morphism, and those are giving us the hypothesis of our theorem. So we have the Czech homology groups for the ring with coefficients in the constant sheaf of the ring will be isomorphic to the Czech homology groups of the space with coefficients on the constant sheaf for the space. So some remarks here to say that this may be interesting is that it is known that we have a smooth manifold of dimension n. Then there is an isomorphism between the Han cohomology and the Czech cohomology of the space with coefficients in this constant sheaf. It is also known that the dimension of in degree 0 of the Han cohomology corresponds to the number of connected components of X. And finally, it is also known that X is connected if and only if this ring only had trivial idempotent elements. So we have a conjecture here that says that the Czech homology group in degree 0 of a ring, any ring, with coefficients in a constant sheaf is related to the number of idempotent elements of R. So this would be a new way to obtain some kind of algebraic properties over a ring. So to finish, I just want to mention some related work. So we are studying this category of sheaves and quantales not only under cohomological aspects, but also under some logical aspects. So one of the things that we would like to investigate is to understand better the subobject classifier of the category of sheaves and quantales. So first, I remind you how the subobject classifier in the category of sheaves and locales looks like. So it has this form, it is this omega. And we would like to do the same for sheaves and quantales. But our quantales are not idempotent. So when we try to do these, things doesn't work very well. Actually, this not even give us a sheaf anymore. So what we have tried to do is that we defined this Q minus here that takes an element of our quantale. And then when you do this chi minus will be an idempotent element. If this operation kind of commutes with the supremum, we are able to define this omega minus here. And this will be a sheaf. And if the quantale is a local, actually this is going to give precisely the omega, and then we would obtain the subobject classifier. But in the more general framework of quantales, this doesn't give us a subobject classifier. what it does actually is that in some sense it essentially classifies a certain class of monomorphisms. So it's not that good, but at least it's something. But we also have tried to define something that is like a K plus here, again, sending to idempotent elements. But to be able to define these, our quantales should have a lot of extra properties. And we have to add even more properties to define, to have that this omega plus is a sheaf. But under that good enough quantale, we are going to obtain that this omega plus actually is a subobject classifier. So this is one of the things we are doing regarding this category of sheaves and quantales. And some conclusions is that we extended the theory of sheaves and locals in the way that the category of sheaves and quantales is not a topos in general. We extended Čech cohomology, showing the potential of the theory to relate algebraic and geometric properties. We have mentioned some logical aspects of this category of sheaves and quantales, and actually something that we are interested is in defining, using those categories for in the future, define some kind of more general notion of elementary topos. And our guess is that the internal logic should change too. And finally, in my thesis, I have developed an extension of sheaves for growth integer topologies in a way that encompasses sheaves on quantales. So some reference here that I have been using, I would like to highlight this work from some of my collaborators that works with this other kind of category of sets with values on quantales. And I hope to use their category to improve our future definition of a more general notion of an elementary topos. Finally, my PhD thesis is this one, and I have an archive about the more logical aspects of this category of sheaves and quantales. So thank you again for this space.
Thank you, Anna. Let's thank our speaker. And are there any questions?
I have a question.
Go ahead.
Yeah, well, originally I had two questions, but you've kind of answered both of them in the last two slides. But I was going to ask about like what this becomes if not a topos, and how it behaves with how it relates to like sort of Grothendieck topologies. But maybe I'll just ask about the latter. You mentioned that you extended the notion of like sheaves with like a Grothendieck topology in a site to quantales. Could you say a few words about like what that extension is, how it looks?
Yeah. Basically, what is happening is that when you come back to the definition of sheaves and quantales, right? The product, when you're working with locals, the infimum is a pullback in the category. But for quantales, this is not a pullback anymore. And so what we're doing, but this is a monoid operation. Mm-hmm. So we constructed something that we call a pseudo pullback. It's not difficult, but the idea is if you have a Cartesian product of two objects, and you take, and then they project for two, like, so A product B goes to A in one side and B to the other, and both goes to an object C. When you take the equalizer of this, we obtain a pullback. But now imagine that we don't work a categorical product, but we have just a tensor product. So we have a monoidal category. If this category is semi-Cartesian, we can have an equalizer again. So this is what we call a pseudo pullback. So the idea is to try to replace the pullback stability by some kind of pseudo pullback stability, but it's not like this. We have to kind of break this third axiom into for things to work properly. I know it's quite often not a good explanation, but more than this is just to have everything.
Okay, and just like maybe an extension to that as well, these notions of like semi-Cartesian, idempotent, and such, are there like restatements of this in that more general structure? Like a similar statement about semi-Cartesian plus idempotent means it actually is pullbacks or something.
Yeah.
Okay, cool. Thanks.
Go ahead, Simon.
Yes. Can you hear me?
Yep.
Yep.
Yeah. So the construction of like the topos of sheaves on a frame or locale, it has a kind of universal property. Like if I have a frame morphism from my frame to the subobject of one in a topos, then it extends uniquely to a geometric morphism. Have you considered if there is a similar universal property of your construction of the category of sheaves on a quantale?
It's on my plans. I wasn't able to find some kind of proof about this yet, but yeah, it would be nice to have something like this. Unfortunately, I don't have it.
Okay, thank you.
Other questions? Everybody's good? Okay, so let's thank the speaker again.
Thank you.